A brief history of machine learning. Machine learning, a subset of artificial intelligence, has roots dating back to the mid-20th century. Here's a brief history. Early concepts, 1950s and 1960s. The field of machine learning emerged from the intersection of computer science and statistics. Pioneers like Alan Turing and Marvin Minsky laid some foundational concepts. Turing proposed the idea of a learning machine in 1950. Rise of neural networks, 1940s-1970s. Inspired by the structure of the human brain, artificial neural networks, ANNs, were developed. The perceptron, one of the earliest neural network models, was created by Frank Rosenblatt in 1957. Symbolic AI dominance, 1960s-1980s. During this period, symbolic AI, which uses logical rules to manipulate symbols, was predominant. Machine learning faced setbacks due to limitations in computational power and data availability. Connectionism resurgence, 1980s-1990s. Interest in neural networks resurged with the development of backpropagation, an algorithm for training multi-layer perceptrons. This led to significant advancements in pattern recognition and other domains. Support vector machines, 1990s. Vladimir Vapnik and Corinna Cortes introduced support vector machines, SVMs, a powerful algorithm for classification and regression tasks. SVMs gained popularity due to their strong theoretical foundations. Big data era, 2000s, 2010s. The proliferation of the Internet led to a massive increase in data generation, enabling the training of more complex machine learning models. Techniques like deep learning, which involves training deep neural networks with many layers, became feasible due to the availability of large datasets and computational resources. Deep learning revolution, 2010s present. Deep learning techniques, particularly convolutional neural networks, CNNs, for image recognition and recurrent neural networks, RNNs, for sequential data, have achieved remarkable success in various applications such as computer vision, natural language processing, and speech recognition. Advancements in reinforcement learning, 2010s present. Reinforcement learning, a branch of machine learning concerned with decision-making and control, has seen significant advancements, particularly with algorithms like deep Q networks, DQN, and deep reinforcement learning. AI in the industry, 2010s present. Machine learning and AI have become integral parts of many industries, including healthcare, finance, transportation, and entertainment. Companies utilize machine learning for tasks such as personalized recommendations, fraud detection, and autonomous driving. Ethical and societal implications. With the increasing integration of AI into society, ethical considerations regarding bias, privacy, and job displacement have become prominent. Efforts to address these concerns and develop responsible AI systems are ongoing. Machine learning continues to evolve rapidly, driven by advancements in algorithms, data availability, and computing power, promising further breakthroughs and applications in the future. Perceptron. The perceptron is one of the simplest types of artificial neural networks, inspired by the biological neuron structure and functionality. It was developed by Frank Rosenblatt in 1957. The perceptron is a single-layer neural network that can be used for binary classification tasks, such as determining whether an input belongs to one class or another. Here's how the perceptron works. Inputs. The perceptron receives input signals, each of which is multiplied by a corresponding weight. These inputs and weights represent the features of the data being processed. Summation. The weighted inputs are summed together with a bias term. Mathematically, this is represented as the dot product of the input vector and the weight vector plus the bias. Activation. The sum is then passed through an activation function, often a simple threshold function. If the sum exceeds a certain threshold, the perceptron outputs a value representing one class, otherwise it outputs the other class. Training. The perceptron learns by adjusting its weights based on the errors it makes during training. The weights are updated to reduce the difference between the predicted output and the true output for each training example. This process is typically accomplished using a technique called the perceptron learning rule, which adjusts the weights in the direction that reduces the error. Perceptrons have limitations, such as their inability to learn nonlinear patterns and their sensitivity to the choice of activation function. However, they laid the groundwork for more advanced neural network architectures, such as multi-layer perceptrons and deep neural networks, which can learn complex patterns and relationships in data. The perceptron model typically consists of a single layer, known as the input layer, and an output layer. It does not have any hidden layers. Therefore, a perceptron is considered a single-layer neural network. The lack of hidden layers distinguishes the perceptron from more complex neural network architectures, such as multi-layer perceptrons, MLPs, or deep neural networks, DNNs, which include one or more hidden layers between the input and output layers. These hidden layers enable the network to learn more complex patterns and relationships in the data. Multi-layer perceptrons, MLPs, and deep neural networks, DNNs, are both types of artificial neural networks used in machine learning and deep learning. While they share similarities, there are also key differences between them. Depth. MLPs have at least one hidden layer between the input and output layers. They can have multiple hidden layers, but they are still relatively shallow compared to DNNs. DNNs are characterized by their depth, meaning they have multiple hidden layers stacked between the input and output layers. They typically have more layers compared to MLPs. Representation power. MLPs can learn complex patterns in data, but may struggle with very high dimensional or nonlinear datasets. They are effective for a wide range of tasks, but may not generalize well to extremely complex problems. DNNs have significantly greater representation power due to their deeper architecture. They are capable of learning intricate and abstract features from data, enabling them to tackle more complex tasks in datasets. DNNs excel in tasks such as image recognition, natural language processing, and speech recognition. Training complexity. Training MLPs is typically less computationally intensive compared to training DNNs. However, as the number of hidden layers or neurons increases, training time and complexity may also increase. Training DNNs, especially very deep networks, can be computationally demanding and require substantial resources, including powerful hardware and large datasets. Techniques like stochastic gradient descent with backpropagation and regularization methods are commonly used to train DNNs effectively. Overfitting. MLPs are susceptible to overfitting, especially when dealing with complex datasets or insufficient training data. Regularization techniques such as dropout and weight decay are often used to mitigate overfitting in MLPs. DNNs. DNNs, especially deep networks, are prone to overfitting due to their high capacity for learning intricate details from the data. Regularization techniques and other strategies, such as batch normalization and early stopping, are essential for preventing overfitting in DNNs. In summary, while MLPs and DNNs are both neural network architectures used for supervised learning tasks, DNNs stand out for their depth, increased representation power, and ability to handle complex datasets and tasks. However, they also come with challenges related to training complexity and overfitting, which need to be carefully addressed during model development and training. The list of algorithms. Providing a full list of machine learning algorithms is challenging because the field of machine learning is vast and continuously evolving, with new algorithms and variations being developed regularly. However, I can give you a broad overview of some of the most widely used and well-known machine learning algorithms across different categories. Supervised learning algorithms. Linear regression. Logistic regression. Decision trees. Random forests. Support vector machines, SVM, k-nearest neighbors, KNN, naive Bayes. Gradient boosting machines, GBM. Neural networks, including multi-layer perceptrons. Unsupervised learning algorithms. K means clustering. Hierarchical clustering. Gaussian mixture models, GMM. Principal component analysis, PCA. Independent component analysis, ICA. T-distributed stochastic neighbor embedding, TSNE autoencoders. Semi-supervised learning algorithms. Self-training. Co-training. Label propagation. Reinforcement learning algorithms. Q learning. Deep Q networks, DQN, policy gradient methods. Actor-critic methods. Proximal policy optimization, PPO. Deep deterministic policy gradient, DDPG. Dimensionality reduction algorithms. Principal component analysis, PCA. Singular value decomposition, SVD. Independent component analysis, ICA. T-distributed stochastic neighbor embedding, TSNE. Linear discriminant analysis, LDA. Ensemble learning algorithms. Bagging. Bootstrap aggregating. Boosting, ADA boost, gradient boosting. Stacking. Random forests. Voting classifiers. Deep learning algorithms. Convolutional neural networks, CNN. Recurrent neural networks, RNN. Long short-term memory, LSTM. Gated recurrent units, GRU, transformer models. Generative adversarial networks, GAN. Variational autoencoders, VAE. Anomaly detection algorithms. Isolation forest. One class SVM. Autoencoder-based methods. Density-based spatial clustering of applications with noise, DBSCAN. Instance-based learning algorithms. K, nearest neighbors, KNN. Learning vector quantization, LVQ. Self-organizing maps, SOM. Evolutionary algorithms. Genetic algorithms. Genetic programming. Evolution strategies. This list covers some of the most commonly used and influential machine learning algorithms across various categories. However, there are many other specialized algorithms and variations within each category that cater to specific problem domains or research areas.